Misha, my friend, I hear you've been analyzing people's invisible movements. Are we talking secret agents or just overly caffeinated colleagues?
It's respiration monitoring, Yogic, non-contact. We're extracting physiological signals from subtle, minute motion, even through clothing or blankets.
Ah, the motion-based method. So my chest movements aren't just me doing a subtle, dramatic shimmy, they're data.
Precisely. One approach uses something akin to optical flow, tracking minute pixel movements across the region of interest, ROI. We then use pixel flow decomposition to mathematically isolate the respiratory component from all that background shimmy.
So you're filtering out the distracting noise, like separating the lead singer's voice, the breathing, from the drummer who hits everything too hard, my nervous twitching. Clever. What about that profile correlation?
That's where we take a vertical slice, or a profile, of the chest ROI in each video frame, and then correlate how that profile shifts over time. It gives us a strong, clear time series signal representing inhalation and exhalation.
So you're basically creating a cross-section, checking how much the bread dough is rising frame after frame. If the dough stops moving, we have a problem.
Exactly. And what's interesting is that the primary direction of that motion, the respiratory angle, is strongly tied to a person's posture.
Ah, so the breath doesn't just go in and out, it has attitude. It helps you with pose estimation.
It does. By analyzing the motion components in both the X and Y directions, we can estimate the subject's posture, sitting, lying on their side, without needing to see their actual body skeleton. It works even when they're covered by a blanket.
Wait, you can tell if I'm sleeping on my stomach just by monitoring the blanket's little up and down dance? That's like psychic laundry analysis. No data training required either. Pure physics deduction. I love it.
Moving on to a different modality, thermal imaging. Here, we measure respiration by detecting the temperature variation induced by the airflow around the nostrils and mouth.
You're using the tiny blast of warm air from my nose as a signal flag. But isn't that signal incredibly weak, especially if I move?
It can be sensitive to the viewing angle and distance, but we found a brilliant hack, especially relevant today, using a facial mask.
A mask? The very thing that hides the flow?
It turns the whole mask into a measurement ROI. The exhaled breath heats the fabric, greatly increasing the area of thermal variation. The mask acts as a thermal amplifier, boosting the signal significantly.
A biosignal booster. That's genius. So if the ROI gets bigger and brighter, you can use cheaper, low-resolution cameras like those little thermopile arrays.
Precisely. We've managed to get clear respiratory signals even at 50 centimeters distance using a low-res thermal sensor because the mask concentrates the heat change. This makes fast screening possible, integrated into things like security gates.
So now the gate doesn't just check my body temperature, it checks my breath depth and rhythm. Talk about compliance screening.
And finally, we can use these thermal patterns not just for rhythm, but for classification, specifically telling the difference between nose breathing and mouth breathing.
The holy grail of sleep medicine. Why is that so hard?
They produce fundamentally different thermal patterns around the nose and mouth ROI. Using feature descriptors, like histograms of oriented gradients, we can mathematically capture the characteristics of these two distinct flow patterns.
You are literally analyzing the statistical puff pattern to figure out which orifice is doing the work. This moves beyond simple vital signs into true habit assessment. You can tell someone, statistically, you are a mouth breather 40% of the night, based on your heat map.
The ability to differentiate these patterns in a non-contact way is a novel diagnostic tool, offering an early indicator for health issues often exacerbated by mouth breathing.
Misha, you've taken movement and heat, mixed them with trigonometry and matrices, and somehow solved the problem of chronic allergies and bad habits. Now, if you could just find a way to make sure I don't eat midnight snacks, we'd be truly unstoppable. Misha, I saw you staring intensely at a grainy video of a person's chest. Are we studying the subtle art of shirt wrinkle patterns, or is there some serious data science hidden there?
It's serious data science, Yojic. We're looking at remote photoplethysmography, or rPPG, applied to respiratory monitoring. We are monitoring the subtle chest emotions induced by breathing to calculate the respiration rate.
So, my chest movements are basically a giant, slow-moving bar chart that you watch with a camera.
That's one way to put it. When a subject breathes, their chest expands and contracts. Even though this motion might be subpixel, meaning it's too small for the naked eye or a simple motion tracker to register reliably, it creates a tiny shift in the brightness and color of the pixels on the skin or clothing.
Ah, the invisible signal. But if it's subpixel, how on earth do you pull a clear periodic signal out of the overwhelming chaos of video compression, random body twitches, and the sheer mediocrity of my t-shirt fabric?
That's the magic of signal processing. We isolate a region of interest on the chest, then analyze the temporal variations in the intensity within that region. We often use techniques like blind source separation, or BSS, or frequency analysis to decompose the composite signal.
Decompose, right. So you're separating the real signal, breathing, from the junk signal, my pulse, my fidgeting, the building shaking slightly. It's like being a DJ who only keeps the clean bass line.
Precisely. The respiratory signal is periodic, typically falling within a known frequency band, around 0.1 to 0.5 hertz for adults. By filtering the data and looking for the dominant peak in that band, using tools like the fast Fourier transform, or FFT, we can accurately determine the respiration rate.
The FFT is the ultimate party pooper, turning my spontaneous breathing into a clinical peak frequency. But does this method actually amplify the movement, or just the resultant color or intensity changes?
The term amplification here refers to the signal amplification. We don't visually enlarge the physical chest movement, but we algorithmically boost the extracted signal features related to that movement. This makes the periodic rhythm stand out clearly against the noise floor.
Got it. So if I'm breathing shallowly and the movement is negligible, the algorithm is still clever enough to find that weak little rhythm buried in the noise and shout its frequency out.
Exactly. And because this is entirely vision-based, we can monitor subjects continuously and non-invasively, whether they're sitting in a home office or resting in a clinic. It requires nothing more than a standard camera and strong computing power.
Continuous, non-contact, and utterly judging my lung capacity. It's like a passive-aggressive digital doctor. Misha, you data scientists are taking all the fun out of hiding my poor health habits. Misha, I'm impressed you can find a subtle sine wave in my chest video. But what happens when I fidget? My breathing may be rhythmic, but my anxiety certainly is not.
Ah, the dreaded motion artifacts, Yoshik. They are the primary nemesis of any vision-based vital sign monitoring. A simple scratch or head turn introduces high-amplitude, non-physiological noise that completely drowns out the subtle breathing rhythm.
It's like trying to listen to a quiet podcast while someone is slamming doors right next to you. How do you silence the door slammer?
We employ several strategies. First, we use robust tracking algorithms to lock onto the ROI and mitigate small shifts. More critically, we implement temporal segmentation and artifact detection. If the movement energy exceeds a certain threshold within a processing window, typically a few seconds, that segment of data is flagged as unreliable.
So you throw away my moments of spontaneity. You only accept the calm, clinically correct portions of my life.
For physiological accuracy, Yes. We prioritize data where the only significant periodic motion remaining after filtering is the respiration itself. Another key challenge for remote sensing is environmental stability. Illumination.
Illumination. If I move from sunlight to shadow, does my respiration rate suddenly change? Because sometimes my boss walks by and casts a massive shadow over my desk.
That change in brightness dramatically alters the pixel intensity, which our camera relies on. We must apply illumination compensation and model normalization to ensure that we are measuring signal changes caused by physiological dynamics, not external light fluctuations. We essentially try to filter out the ambient light color from the physiological color shifts.
It's a constant battle against the sun and bad office lighting. Given all these hurdles, fidgeting, shadows, bad shirts, how close is your non-contact rate to what a traditional gold standard sensor would measure?
In controlled studies, our systems demonstrate high accuracy, often measured using the root mean squared error, RMSE, compared against clinical devices like chest bands or impedance pneumography. We aim for an RMSE below 1 breath per minute. Robust validation across different skin tones and body types, the generalization challenge, is paramount for clinical adoption.
1 breath per minute error? That's tighter than my deadline schedule. So, you're confirming that the future of vital sign monitoring is quiet, invisible, and powered by advanced math.
The ultimate goal is to provide continuous, ambient, and clinically reliable monitoring without burdening the patient with wires or wearables. It's about making the environment itself a passive sensor.
Brilliant. I'll tell my therapist I'm not fidgeting. I'm generating noise artifacts for temporal segmentation practice.
The latest trial data on motor cortex control is fascinating. We're finally optimizing the signal-to-noise ratio to a point where the latency is negligible. Think real-time thought to action.
Real-time thought to action. So, instead of accidentally sending a text message containing only the word soup, I'll accidentally buy stock in an artisanal soup company using only brainpower? Progress.
That's pessimistic. We're talking about restoring function, increasing human bandwidth. The current brain-to-interface data rate is pathetically slow compared to what the hardware can handle. We're addressing that bottleneck.
I don't want my bandwidth increased. I already receive too many emails. Imagine receiving thoughts from strangers just because you're in the same Starbucks Wi-Fi range.
It's not public broadcast, Yogic. It's a targeted interface, mostly for therapeutic or augmentation purposes. You won't accidentally stream your inner monologue about why airplane pretzels are a crime against texture.
Oh, but I absolutely will. Misha, the second we digitize the self, we introduce bugs. What happens when your inner existential scream gets compressed into a tiny, irritating .zip file that won't open?
We'd have a patch. We're talking about precision engineering. Imagine being able to access tertiary data without the tedious processing time of language. Pure concept transfer.
Pure concept transfer? That's terrifying. It means I can't hide my sheer lack of understanding of, say, the geopolitical complexities of the South China Sea. Currently, I use vague hand gestures and the word crucial. That's social lubricant.
You are arguing for the inefficiency of human communication as a defense mechanism.
I am arguing that inefficiency is often the only thing standing between us and total mental collapse. Plus, think of the advertisements.
The what?
The ads. You install a neural net, and suddenly your internal monologue is interrupted by a shimmering blue pop-up asking, "Are you sure you don't want to upgrade your subscription to premium consciousness?"
That's a network security problem, not a neuroscience problem. We can filter the data stream. We're focused on optimization. Imagine the ability to archive memories perfectly.
and then accidentally share them to a private company server because you clicked accept all cookies on a mental EULA you didn't read while contemplating the perfect martini. No thank you. I like my memories fuzzy, filtered by shame, and conveniently inaccessible. It's called self-preservation.
But the precision. Think of the efficiency of academia. A historian could experience a day in ancient Rome via perfect recall, transmitted instantaneously.
And then that memory stream gets targeted with a truly uncanny ad for sandals they wore during the reign of Augustus. People who downloaded the Punic Wars also purchased these distressed leather slippers.
All right. I concede the advertising model is perhaps the ultimate inevitable dark pattern of all technology. But let's look at the hardware. We're exploring biocompatible polymers that
Biocompatible polymers. See, that's where you lose me. I prefer my tech to be visibly metallic and slightly dangerous, like a toaster. When my toaster acts up, I can yell at it. When my brain implant starts serving me 5-second pre-roll videos before I can form the thought coffee, who do I complain to? Customer service?
if your neural interface provided poor service, you'd file a mental support ticket.
And they'd respond with, "Thank you for contacting support. Did you try restarting your consciousness?" And then I have to shut down my whole operating system for 48 hours just to clear the cache of anxiety.
Maybe the real benefit of the implant isn't processing speed, but the ability to install a sophisticated internal spam filter that categorizes existential dread as promotional.
Now that is innovation. But only if I can label every notification from my mother as junk mail, highly suspect. So, Misha, in terms of actual implementation, when do you expect this fully integrated neurodigital existence to be common?
5 to 10 years for advanced therapeutic widespread use. 20 years for robust consumer augmentation that reliably improves cognitive function without the risk of, say, your operating system crashing when you try to juggle 3 thoughts simultaneously.
So, just enough time for me to get used to my own brain, and then I'm supposed to download an update that completely changes the UI. No, thank you. I'm waiting for the retro analog brain interface. Just a nice dial, maybe some vacuum tubes. I want to feel the heat of my own inefficient processing.
You want the steam-powered brain, Yujik.
Precisely. Less bandwidth, but excellent aesthetic and a comforting aroma of coal and delayed existential horror. Now, if you'll excuse me, I'm going to go stare blankly at a wall just to keep my input streams pure and analog.
Enjoy the zero latency experience of boredom.
Always do. It's the only truly unmonetized mental state left. For now.
Cadê bala desse
You look twitchier than usual. Did the coffee machine try to implement QRS detection on your heart rate?
Funnier. I was reading Misha's musings on machine learning, specifically the chapter on closed-loop pacemaker algorithms. Why your heartbeat is just another time series to me. I'm not twitchy. I'm optimizing my R peak detection threshold.
Excellent. So you understand we're discussing the ultimate real-time control system. Not just if you need a beat, but when and how hard. Predictive maintenance, but for your myocardial tissue.
I get the elegance. Instead of fixed-rate pacing, the equivalent of a metronome set by a guy who only listens to marching band music, you're adapting. It's like improvisational jazz, but if the saxophone player passed out, the drum machine immediately takes over, using the key signature he established 2 bars ago.
Exactly. The closed loop. The gold standard used to be VVI or DDD pacing. Relatively dumb. Now, the device is an embedded data scientist. It consumes the ECG, analyzes the PQR-ST complex, understands the patient's intrinsic rhythm, and decides if it needs to intervene. It's a perpetual A/B test running on your ventricles.
So, if a pacemaker has an internal clock that's way more accurate than my grandpa's $10 Timex and is constantly measuring performance metrics, heart rate variability, depolarization morphology, is the pacemaker depressed if it finds out its user has terrible data quality?
Low SNR, patient exhibiting ventricular flutter, device size dramatically. It's a risk. But think about the feature engineering here, Yozik. We're not just looking at amplitude, we're using sophisticated classifiers, sometimes even deep learning models on the chip to differentiate between artifact, a genuine intrinsic beat, and a potentially fatal arrhythmia.
Deep learning on the chip? So my heart isn't just being monitored by a simple thermostat. It's being run by a tiny silicone oligarch making split-second decisions about my mortality. Does it require a minimum viable GPU?
Efficiency is key. Power consumption is the ultimate constraint. You can't run GPT-4, but you can run a highly optimized lightweight convolutional neural network or a specialized support vector machine for pattern recognition. We need precision, but a battery life of 10 years is non-negotiable. It's the ultimate trade-off between computational power and biological persistence.
It's a masterclass in minimalism. Like a comedy set where every word is necessary, and if you remove one joke, the audience dies. Speaking of necessary jokes, what happens when the closed loop overfits the data?
Oh, that's a terrifying scenario.
Imagine, the patient is sitting still, the device learns their specific T-wave morphology so perfectly that when they get up to grab a beer, the slight electrical change from muscle movement is interpreted as a malignant event, and the pacemaker unleashes a 9-volt shock, purely out of misclassified zeal.
That's why robustness against noise and generalization are vital. The algorithms are trained on massive multi-ethnic datasets featuring every flavor of cardiac anomaly. We're teaching it to recognize the signal of impending doom, even when the signal is drowning in electromyographic noise from excessive yawning.
So the closed loop doesn't just treat the heart, it models the user's life. If I suddenly decide to become a marathon runner, does the pacemaker text my cardiologist? Anomaly detected. User is exercising, flagging behavior change.
Absolutely. The newer generations include accelerometer data and respiration sensors. They recognize activity. Did the person stand up? Are they walking? Are they stressed? Measured partly through heart rate variability. This allows the pacemaker to adjust its pacing rate dynamically. It's literally running a dynamic regression model on your level of physical exertion versus required cardiac output.
Wait. So the machine knows I'm lying when I tell my doctor, oh yes, I walk for an hour every day. It's gathering the evidence.
Data never lies, Yozik. Your pacemaker has a little log file titled userlies.csv.
This is too much power for an autonomous medical device. Next, they'll be installing Bluetooth connectivity so we can argue with my smart fridge about whether I should eat that leftover cake.
We call that the cardiologist remote monitoring pathway. It's secure, encrypted, and HIPAA compliant. And yes, it absolutely monitors adherence to dietary suggestions indirectly via resting heart rate variability and weight data, if integrated.
So my tiny metallic heart servant is also my life coach and my most accurate biospy. The loop is closed, Misha. The data stream is flowing. My life is quantified, optimized, and externally managed. I feel simultaneously safer and profoundly less free.
Welcome to the future of data-driven biology, Yozik. Don't worry, if you code your pacemaker to ignore my suggestions, I'll just have to implement an adversarial training loop to convince it otherwise.
Is that how the war between human will and AI control begins? With one data scientist trying to optimize a comedian's resting heart rate?
It starts with a well-timed, algorithmically determined ventricular contraction. Now breathe. The device is currently classifying your current elevated anxiety as amusement artifact. Don't ruin the data set.
Fine. But if this thing ever tries to autocorrect one of my jokes, I'm pulling the lead.
Typing rapidly. Logging user threatens hardware integrity. Pacing rate stable. Good talk, Yozik. Look, you keep focusing on the comedic existential dread. I'm focusing on the technical nightmare of real-time processing with extreme power constraints. That closed loop, it needs to operate within an incredibly tight decision horizon.
The decision horizon. Sounds like the title of a terrible sci-fi movie where the hero has 150 milliseconds to decide whether to zap the alien or just pace its tachycardia.
Pretty close. If the natural PR interval, that time between atrial depolarization and ventricular depolarization, is, say, 120 to 200 milliseconds, our algorithm has to consume the atrial signal, determine if the ventricles are failing to fire, calculate the required energy level, and deliver the impulse before the VFib threshold is hit. We're talking latency requirements that make high-frequency trading look leisurely.
So if the machine decides too late, the patient is essentially blue-screened. Is there a built-in Control-Alt-Delete feature, or do we just call that defibrillation?
That slow reaction time, high latency, leads to undersensing, or worse, delivery of a pulse during the heart's natural refractory period, which can be catastrophic. The signal processing pipeline is brutal. Raw EGM acquisition, filtering, baseline wander removal, R-peak detection, morphology classification, and then the pacing decision logic, all running on a few milliwatts. If the filter is too complex, it increases latency and drains the battery. If it's too simple, you're oversensing elevator noise.
Oversensing, my favorite technical flaw. That's when the device misclassifies non-cardiac electrical activity, like chewing gum, muscle tremor, or electromagnetic interference from the hospital MRI scanner as a legitimate beat. Essentially, the pacemaker has performance anxiety and keeps firing pulses when the heart is already working fine.
Precisely. And the computational challenge is filtering out that non-cardiac noise without simultaneously smoothing out or delaying a truly critical arrhythmia signal. We use adaptive thresholds that fluctuate based on the preceding R-wave amplitude, trying to dynamically optimize the signal-to ratio. But those thresholds introduce their own calibration problems.
Calibration problems? You mean long-term stability? Misha, these devices are supposed to run reliably for a decade. Human biology is messy and prone to decay. The electrode moves, the tissue fibrosis, the impedance changes. How does your closed loop compensate for the fact that the actual sensor environment is physically changing in a wet, corrosive biomechanical soup?
That's where the unsupervised learning component becomes both necessary and terrifying. The device must continuously monitor lead impedance and the depolarization threshold, the minimum energy required to capture the ventricle. It constantly runs low-level test pulses to find this threshold and dynamically adjust the pacing amplitude. This is essential for battery life. Why waste energy delivering 3 volts when 1.5 volts will do?
Wait, so you are confirming that this silicon despot is self-teaching and auto-calibrating inside my body? It's constantly performing micro-experiments to improve its efficiency.
This means the pacing parameters, the very thing keeping me alive, are slowly drifting away from the original physician-set parameters. What if the model drifts into a locally optimal, globally fatal configuration?
Model drift is a critical concern, especially regarding long-term reliability. We try to bound the parameter space, preventing drastic shifts, but if the biological environment changes significantly, e.g. severe lead fracture or perforation, the algorithms might struggle to adapt safely, leading to misclassification of rhythms or delivery failure. That's when the remote monitoring pipeline becomes crucial.
Ah, the data exfiltration pathway. Let's talk about that pipeline, Misha. You're sending highly personal, millisecond resolution physiological data, the literal blueprints of my electrical mortality, over the public internet. Forget HIPAA compliance. Let's talk about the integrity of that data in transit. If an attacker intercepts and modifies the data before it hits the remote server, introducing phantom PVCs, for instance, could they manipulate the physician's understanding of my condition?
The communication protocols are layered with robust encryption and authentication, designed to prevent replay attacks and data tampering. However, the theoretical vulnerability lies not just in the data in transit, but in the edgy computing environment, the pacemaker itself. If an attacker exploits a vulnerability in the pacemaker firmware, they could corrupt the self-learning model or force a denial of service attack on the pacing function.
So, my closed-loop pacemaker, this tiny algorithmic genius, isn't just subject to physical decay, electrical noise, and high-stakes latency, but also to the risk of being bricked by a bored teenager in Belarus. The final irony of the quantified life, our optimized cardiac function becomes a zero-day exploit target.
It's the ultimate ethical dilemma in medical IoT. We need the connectivity for life-saving remote intervention and optimization, but every new line of code, every wireless antenna, represents an increase in the attack surface. The very algorithms designed to save you by precision control are the vectors through which catastrophic error can be introduced. The loop is closed, Yojic, and it's surrounded by firewalls we hope hold up for a decade.
Hope is a terrible debugging strategy, Misha. I prefer robust, peer-reviewed existential despair. Pass the data logs. I want to see exactly how often my life is being threatened by noise filtered by an algorithm constrained by a lithium battery.